Now we go for question number 5, which is also very important theory about finding magnetic field produced by extremely thin current carrying circular ring. How to find? I am showing you. Consider extremely thin current carrying circular ring with radius small a and having its plane perpendicular to plane of the figure. Plane of the figure is this, perpendicular to that means like this. So you are supposed to consider the plane of that ring like this. Got it? Fine. Now for this ring, this is its geometrical axis, meaning thereby that axis is perpendicular to the plane of the ring as well as it is passing through the center of the ring, correct? And that geometrical axis is at present, suppose x axis. Here I have written axis of the ring. Got it? Now just pass current through that ring, suppose in this direction, correct? And this part is on the back side of the axis, on the back side, then I am showing it by dotted curve, and this part on the front side of the axis, which I am showing by a solid curve. Got it? So current is flowing this way. If current is flowing this way, then you are supposed to find out magnetic field produced by such a current carrying extremely thin circular ring at some axial point, means at some point on the axis, and that point of the axis I am taking here, say point P, which is right now point of observation, and that point is at distance x from the center of the ring, correct? At the center we have considered origin. Got it? Fine. Now first of all you do one thing, you select one current element at this topmost position, and that current element is I vector dl, correct? Can you guess the direction of this current element? Perpendicularly outside the plane of the figure. Why? Look, if that ring is like this, correct, current is flowing this way, and now at this topmost position if you consider current element, suppose that current element is like this, correct, then it is like this in the direction of current, tangentially at this point. So it is perpendicularly outside the plane of the figure, correct? Fine. And similarly, if you consider one more current element diametrically opposite end, at the diametrically opposite end, then because the current direction is now here perpendicularly inside the plane of the figure, that direction of current element will also get reversed this way, correct? And that current element I have also shown here. This is perpendicularly outside the plane of the figure, this is perpendicularly inside the plane of the figure. Got it? Fine. Now with respect to this current element, the position vector of this very point is vector r, correct? And now tell me, in this right angle triangle, this is hypotenuse and these are the two perpendicular sides. Apply now Pythagoras theorem, r square will be equal to a square plus x square. Here it is, r square equals to a square plus x square. Take power 3 by 2 on both the sides. So it is power 3 by 2 here also, here also. Now when you multiply these two powers, 2 will cancel, giving you r cube, and this part as it is, okay? Now due to this current element, the magnetic field produced at this very point according to B.S.SHAH's law is suppose vector dB, and then according to B.S.SHAH's law, what is vector dB? By formula mu 0 I upon 4 pi into vector dl cross vector r upon r cube, vector dl cross vector r upon r cube, correct? Now this part as it is, come on, I want now magnitude of this, so I am putting only dB. When you want magnitude of this, come on, magnitude of a cross product, it is multiplication of magnitude of first vector, second vector and sign value of angle between them. Magnitude of first vector is dl, magnitude of second vector is r, and sign value of angle between these two, which is 90 degree. Now try to imagine, try to visualize how that angle is 90 degree. I am showing you. This is perpendicularly outward and this is vector r, correct? Where is vector r? Tell me. On the surface of board, correct? And this I vector dl is coming perpendicularly outside. So what is the angle between these two? Come on. This is direction of vector dl. This is direction of vector r. What is this angle? This is right angle. Situation is like this. Look. This is vector dl and this is vector r. Correct? What is the angle between these two? It is 90 degree. Got it? That's why. Upon r cube as it is, come on, simplify. 1 r will get cancelled, giving you mu 0 I upon 4 pi into dl upon r square. Correct? Now let me find out direction of vector db. Direction of vector db, meaning thereby direction of vector dl cross vector r. Tell me, this is vector dl, this is vector r. This is vector dl, this is vector r. Now think of a plane passing through these two vectors, correct? This is vector dl, this is vector r. Think of a plane passing through these two vectors. That plane is slanting plane, slanting, inclined. And that inclined plane is this. And now you should think of one right-handed screw perpendicular to that plane, and then you must rotate this screw in a manner first vector rotates towards second vector. First vector is vector dl, second vector is vector r. I am supposed to rotate vector dl towards vector r this way, correct? Now, if the same right-handed screw, if I rotate this way, it will advance this way. It will advance in this direction, which is perpendicular to vector r. Don't you know? Direction of a vector product is always perpendicular to both the component vectors. So, direction of this will be definitely perpendicular to vector r. So, perpendicular to this vector r is this direction, which is direction of vector db, correct? Similarly, you can find out now direction of vector db due to this second current element, which is located diametrically opposite, okay? Come on, this will be the situation. This is vector dl, this is vector r, okay? Now, think of a plane passing through these two vectors, and think of a right-handed screw perpendicular to that plane this way. Now you must rotate this screw in a manner first vector rotates towards second vector. First is vector dl, second is vector r. When you rotate vector dl towards vector r this way, correct, then that screw will advance in this direction. In this direction, look, this way, perpendicular to vector r. Got it? Fine. Now just take this angle to be phi. If this angle is phi, this also will be phi. I told you, whatever is the angle between two given line segments, same is the angle between their perpendiculars. Angle between these two line segments is phi, then angle between their perpendiculars also must be phi. Perpendicular to this is this. Perpendicular to this is this, correct? This is vertical, this is horizontal. They have to be perpendicular. And perpendicular to this is this direction. So, angle between these two perpendiculars also must be phi, correct? Similarly, if this is phi, this also will be phi. And these two angles are equal, and these two angles are also equal, okay? Now, just resolve this vector into two mutually perpendicular components. One is this component, another is this component. Correct? They are mutually perpendicular. Fine. But this component is parallel to axis. I am showing by symbol db parallel, which is component of db adjacent to phi, which is db cos phi. db cos phi. Correct? If this angle is phi, this also will be phi, because these two are alternate angles. Correct? Now, how to find this component, which is perpendicular to this axis, shown by symbol db perpendicular? It is component of db, opposite to phi, it is db sin phi, db sin phi. Similarly, this vector also can be resolved into two mutually perpendicular components. One component parallel to axis is db parallel, which is db cos phi. Another component perpendicular to axis, which is db perpendicular, which is db sin phi. Correct? Now tell me, at this very point, how do you find these two components? Equal in magnitude but opposite in direction. They will cancel out each other. Correct? Because such components have equal magnitude in opposite directions, their effects are getting cancelled out, and so whatever magnetic field at point P we will get, it will be solely due to only dB cos phi components, correct, which are parallel to the axis. So if you want resultant magnetic field at point P, you must consider only dB cos phi components which point in the same direction. And whenever vectors are in the same direction, you can make their scalar addition. That's why I am not putting here vector B, I am putting only B, because I know that these components are in the same direction, I can make their scalar addition, okay. And when you make scalar addition of such components, then you will get resultant magnetic field at point P, okay. Here addition means integration of such components, okay. Come on, integration dB cos phi, integration dB value is this much, mu 0 I upon 4 pi into dl upon r square, mu 0 I upon 4 pi into dl upon r square into cos phi. What is cos phi for this right angle triangle? Come on, adjacent to phi, which is small a, which is radius of the ring, divided by hypotenuse, which is opposite to right angle, which is magnitude of this vector, it is r. Adjacent side divided by hypotenuse will give you cos phi. So what is value of cos phi? It is a upon r. Put it here. Cos phi is a upon r. A upon r. Correct? Multiply now. Mu 0 I a upon 4 pi r into r square, which is r cube. Because that part is constant, I just take it out of the symbol of integration, and then it is integration dl in multiplication, okay. Now this part as it is, mu 0 I a, 4 pi as it is. What about r cube? R cube we know it is a square plus x square whole raised to 3 by 2. A square plus x square whole raised to 3 by 2. What about integration dl? Integration dl means summation of lengths of all the length elements considered continuously along the circumference of this circular ring. Naturally, when you add all the lengths of all the length elements which are considered continuously along the periphery of this ring, it will give you circumference of that ring. And don't you know formula for circumference? It is 2 pi r. Better you say here 2 pi into radius. 2 pi into radius. Radius is small a. That's why I am putting here 2 pi into a. Correct? 2 pi into radius. Got it? Now simplify. Pi will cancel. 2 2s are 4. So here it will appear 2. Now it is mu 0 I a into a, that is a square, divided by 2 into a square plus x square whole raised to 3 by 2. Got it? Fine. This is the magnetic field at this very point due to only one circular turn, due to only one current carrying circular turn. But suppose in the same ring there are capital N number of identical circular turns and each of them carries I amount of current, then naturally you will get resultant magnetic field at this point N times this magnetic field which is obtained out of only one turn. Correct? Due to one turn, if this much is the magnetic field, due to capital N number of identical turns, what will be magnetic field? N times. So just multiply this value by N. So I am multiplying by capital N. Okay? And here as this x will change, this also will change. So mathematically you can say this is the magnetic field which is a function of x. So this much magnetic field you will get at distance x, on the axis from the center of the ring. That's why I am putting symbol Bx. So this is the magnetic field at distance x, okay, fine. Here total magnetic field will be along positive x axis, okay. This is not x component of magnetic field, no, here total magnetic field is along positive x axis, got it, fine. Now as x will change, this will also change. Tell me from this formula, if x will decrease, this magnetic field will increase. Now you just select this point at the center. When you select this point of observation at the center, this x will decrease to 0. If selected point is here at the center of the ring, x value will be 0. When x is 0, you can put the symbol B0. That's why I am putting here B0, correct? Because I am talking about magnetic field at the center. Come on, at the center x is 0, so this part will be 0, and when you multiply these two powers, 2 will cancel, it is a cube now, a square upon a cube, so left is a in the denominator, so now it is mu 0 ni upon 2a, here it is. mu 0 Ni upon 2a, correct? One more thing, when this x decreases, this increases. When x value you are writing 0, 0 means minimum, at that time this magnetic field will be maximum, that's why I am putting symbol B maximum, B maximum. So remember, for any thin current carrying circular ring, the maximum magnetic field is obtained at its center among all the points on its axis. Where is the maximum magnetic field? It is obtained at the center. Okay, fine. As you go this way or you may go this way, x value will increase. When x value will increase, come on, this magnetic field will decrease. Okay. Now let us consider one special case. What is a special case? Suppose this point of observation is taken very far on the axis, very far from the center of the ring, very far. If you consider this point very far on the axis, then x value will be very much greater than a. X is very much greater than a. If it is so, x square will be further very much greater than a square. X square is very much greater than a square, then a square will be negligibly small, and if you neglect it in the addition, then left is here x square whole raised to 3 by 2, 2 will cancel, giving you x cube. So final formula will be in that case mu 0 n I a square upon 2 x cube. Come on, mu 0 n I a square upon 2 x cube. Correct? Can you say one thing from here? Bx is inversely proportional to cube of x. Bx is inversely proportional to cube of x. Can you recall something similar result which you had studied in chapter number 1? In case of electric dipole, the electric field at very far axial point or very far equatorial point is inversely proportional to cube of the distance, correct? Similarly here, magnetic field is inversely proportional to cube of the distance, correct? Now, how to get the direction of this vector? If you want to write it vectorially, you may write here vector Bx, correct? But then vector equals to magnitude multiplied by unit vector. Magnitude is this much, same magnitude are written here, multiplied by unit vector. Direction of this vector means direction of these components. And direction of such components, you can see it is along positive x-axis. That's why unit vector is I hat, correct? But then, when is the direction of magnetic field along positive x-axis? Provided in this situation current is flowing through the ring this way, correct? If you revert the direction of current instead of this way, if you allow it to flow this way, then direction of magnetic field is also getting reversed. Instead of positive x-axis, in that case magnetic field will be obtained along negative x-axis. There is one specific rule to determine the direction of magnetic field in such cases. What is that rule? It is called right hand thumb rule. What is it called? Right hand thumb rule. Hold the axis of current carrying thin circular ring. Don't hold the ring. Hold the axis of current carrying thin circular ring in the right hand palm such that fingers should take the turn in the direction of current, and then you find out the direction of thumb shown on the axis. In the same direction there is a magnetic field. I repeat, hold the axis of extremely thin current carrying circular ring in the right hand palm such that the finger should take the turn in the direction of current. Then whatever is the direction shown by the thumb parallel to axis, in the same direction there is a magnetic field produced by that ring. Okay, I repeat once again. Hold the axis of thin current carrying circular ring in the right hand palm such that fingers take the turn in the direction of current. Then whatever is the direction shown by the thumb parallel to the axis, in the same direction there is a magnetic field. Okay, now tell me, if direction of current is this, correct, reverse to this, then you should hold the axis in your right hand palm this way such that finger should take the turn in the direction of current this way, correct? At that time thumb is pointing the direction towards negative x-axis. In the same direction there will be magnetic field. Okay, so what I mean to say, in case of extremely thin current carrying straight wire, the magnetic field lines were circular, and here when the current carrying wire itself is circular, the magnetic field lines are straight, correct? I repeat, if current carrying wire is straight, then magnetic field lines are circular. Now speak opposite. If current carrying wire is circular, then magnetic field lines are straight. Got it? Fine. Come on, my dears. We proceed further in chapter number 4. Now we go for question number 6. It is about magnetic field on the axis of current carrying solenoid. Now first of all, let me introduce what is called a solenoid. My dears, to understand about what is called a solenoid, you please consider a cylindrical coil which is made up of some isolated wire which is very closely wound on some cylinder. Such a device is known as solenoid. It is having a definite shape which is called helical shape. Now you may ask, what is called helical shape? It is like a shape of a spring of a ball pen. All of you have seen the spring of a ball pen. That shape is called helical shape. Okay? So an isolated wire which is wound on some cylinder very closely with a helical shape is only known as a solenoid. Okay? Fine. It is not necessary that you should wind that coil on some cylinder, not necessary. You may wind it in the medium of air, then the central medium which is known as core, it will be medium of air. Okay? So if you have got that sort of solenoid, how will it appear? I am showing you that solenoid. Look, it is something like this. You can see here a coil whose winding is very close, the turns are quite close to each other, and the whole coil is made up of that wire which is electrically isolated. Okay? And it is wound on some cylindrical shape, and such a coil is known as solenoid. Okay? Fine. The turns which are wound on the cylinder, it is called winding of the solenoid. And now what we observe practically, I am showing you. Look. Consider a solenoid as shown in the figure. Now the two ends of that cylindrical coil are these two ends, correct? Now what we do, we connect those two ends with a battery. Fine. Now you can start the current from positive terminal of the battery, and that current will now flow through all the turns of this cylindrical winding, correct? And now you know, whenever there is a current, you know it is a source of magnetic field. So here with the passage of current, what you can expect? You can expect now magnetic field. Yes, you are going to get magnetic field not only inside the solenoid of some finite length, but you will have magnetic field outside the solenoid also. Now here that magnetic field has some definite shape of magnetic field lines which I have shown in the figure. Okay? Here when you pass the current in this manner, correct? When you pass the current in this manner, at that time the magnetic field is arising here, which is having magnetic field lines taking turn as per the diagram. Okay? Similar magnetic field we find around bar magnet. That is what you will be taught in the next chapter. Okay? So this magnetic field and the magnetic field surrounding to bar magnet are identical. So we say sometimes current carrying solenoid behaves like a bar magnet. Current carrying solenoid behaves like a bar magnet. This fact gives you its physical importance. Okay? Fine. Now here the magnetic field lines seem to have emerged from this end, and they form closed loops, and they enter this solenoid through this end. This sort of magnetic field you will have provided you are passing the current as per the diagram. Okay? Fine. Now, how much is the magnetic field inside the solenoid of finite length, its expression we have to derive in our syllabus. Let us derive now. Last time, if you have remembered, we had obtained magnetic field at some axial point which was at distance x from the center of extremely thin current carrying circular ring having capital N number of identical turns. What was that formula? B as a function of x. You may write Bx this way also, where x is the distance of point of observation on the axis of current carrying circular ring from its center. Okay? And the same symbol, I just give another symbol now, B as a function of x. B as a function of x. My dears, don't get confused. It is not a product of B and x. No, it is not a product. Mathematically, this symbol means B as a function of x. Okay, fine. Now that formula was mu 0 n I a square upon 2 into a square plus x square whole raised to 3 by 2. Come on, mu 0 n I a square upon 2 into a square plus x square whole raised to 3 by 2. Correct? Fine. Now what was capital N at the time? Total number of identical turns which are considered in the extremely thin current carrying circular ring. Correct? Fine. Now let us substitute for capital N. In this case, what it can be, I am showing you. First of all, you take cross section of this solenoid this way. Correct? Vertical cross section parallel to the plane of the figure. Correct? If you take that cross section, then the cross section would appear like this. Look, this is the cross section of this solenoid. And now when you take cross section this way, you can see these turns are coming out of the plane of the figure, coming out. Then last time I told you, whichever direction comes out of the plane of the figure perpendicularly, that must be shown with the symbol of dot. That's why I am putting here so many dots. Okay, fine. And then those turns will come out from the upper part, and from the lower part they will get in. They will be going inside the plane of the figure. Correct? And those turns I am showing by the symbol of cross. Correct? I repeat, this dot means perpendicularly outward from the plane of the figure, and this cross means perpendicularly inside the plane of the figure. Correct? Fine. And such winding you are supposed to consider throughout the length of the solenoid. Okay? Right from one end to the another end. Okay? Now, among this total winding, I just select a particular winding with very small thickness. Let it be dx. Correct? Now, if you consider only this much thin part of that winding, it is as good as extremely thin current carrying circular ring. Correct? So, now take this part as current carrying circular ring. For this ring, come on, look in the figure, this much is its radius. Let it be small a. Correct? Now, when you pass current this way, you are going to have magnetic field on the axis in this direction. And that magnetic field I have shown with the symbol vector capital B. Okay? Now, suppose we want to find out that magnetic field at this very point P, which is taken on the axis of the ring at distance x from the center. Correct? Fine. Now, due to this current carrying circular ring at point P, we will have this much magnetic field, this much, where capital N will indicate total number of turns in this ring. Let us find out that. What is the length of this much part? Let it be dx. Now, in this solenoid, throughout its length, if number of turns per unit length is n, then what will be number of turns in length dx? Let us find out. Per unit length, if number of turns is small n, then for length dx, what is the number of turns? This into this upon this. It will be n into dx. N into dx. Correct? So, n into dx will give me right now total number of turns in the considered ring, which earlier we had shown by symbol capital N. Correct? So, at present capital N is n into dx. Okay? replace capital N by N into dx, that's all. This much magnetic field we will have at this point due to this considered ring, correct? But we want actually the resultant magnetic field at this point P due to entire current carrying solenoid. How to find that? I am showing you. First of all, you consider some vertical direction passing through point P. That vertical is this, fine. Now you just join this point with the top of the considered ring, then you will get this line segment, correct? Fine. Now angle made by this line segment with this vertical, I just take it as theta, okay? If this angle is theta, this also will be theta because these two are alternate angles, correct? Now tell me, in this right angle triangle, if you find out tan theta, how much will it be? Tan theta, it is opposite to theta divided by adjacent to theta. Opposite to theta is x, adjacent to theta is radius of this ring, or you can say it is radius of cross section of solenoid, got it? It is small a. Opposite side divided by adjacent side, got it? Now find out x, transfer this a, x equals to a tan theta. Now on both the sides you please take derivative with respect to theta. So when you take it here, it will appear dx upon d theta. Here a you must take constant because whether you consider this ring here or here or here or here, correct? Throughout the length, the radius of that considered ring will remain same and constant. So because a is taken constant, now you can take derivative of tan theta with respect to theta. Last time I told you that derivative formula, d by d theta of tan theta is sec square theta. So I am writing here sec square theta, okay? Find out dx now, transfer this. So dx will be a sec square theta d theta. Now I also require the value of a square plus x square whole raised to 3 by 2. Let me find it out because I would like to substitute here, correct? That is why I am finding that value. A square as it is, x square, from here x square will be a square tan square theta, a square tan square theta whole raised to 3 by 2, correct? A square taken common, inside the bracket 1 plus tan square theta is nothing but sec square theta, correct? Last time I told you about that identity. Come on, 1 plus tan square theta equals to sec square theta whole raised to 3 by 2 as it is. Now when you multiply these two powers, 2 will cancel giving you a cube. When you multiply these two powers, 2 will cancel giving you sec cube theta, sec cube theta. Substitute those values in this formula now. Start with this, b as a function of x, b as a function of x equals to mu 0 n, and now it is dx. Dx formula is a sec square theta d theta, a sec square theta d theta into I into a square, correct? Divided by 2 into, come on, a square plus x square whole raised to 3 by 2. A square plus x square whole raised to 3 by 2 is nothing but a cube sec cube theta, a cube sec cube theta, correct? Now simplify. A into a square will be a cube, that a cube from the numerator and this a cube from the denominator will get cancelled. Sec square theta upon sec cube theta, it will be 1 upon sec theta, and 1 upon sec theta is nothing but cos theta. D theta as it is, and left in multiplication is mu 0 n I upon 2. Here it is mu 0 n I upon 2. Got it? Fine. Now this much will be the magnetic field at this point due to only one such considered ring. But then we want resultant magnetic field at the same point due to entire solenoid. For that what you can do? You can think of such many continuously arranged rings right from left end to the right end, okay? And each time you can find out such partial value of magnetic field, and then after you are going to take vector addition of those partial magnetic fields. Naturally you will get resultant magnetic field, correct? At point P, let it be capital B, which is nothing but summation of partial values of magnetic field. Why I am taking here scalar addition? Because when you pass current through the winding of solenoid this way, due to each considered circular ring, you will have magnetic field in the same direction. And because all such partial values of magnetic field are in the same direction, you can make their scalar addition, correct? And that addition we find out by taking integration. This B as it is, integration as it is, value of B as a function of x. Value of B as a function of x is mu 0 ni upon 2 into cos theta d theta. Mu 0 ni upon 2 into cos theta d theta. But now take care how to put the limits of this integration. I am showing you. See here variable is in terms of theta. So you must specify the limits also in terms of theta. Lower limit of integration means smallest value of the variable, and upper limit of integration means highest value of the variable. Okay, how to find out those limits I am showing you. First of all, you think of joining this point P with the upper left end, okay, and find out angle made by this line segment with this vertical, and that angle will be this. But because that angle is on left side, I just take it with the negative sign. Let it be minus alpha 1. Similarly, join point P with the upper right end of the solenoid, and then find out angle made by this line segment with this vertical, and because that angle is on right side, I just take it with positive sign plus alpha 2, correct? Tell me, why is there a negative sign here? Just to identify the position of the considered ring. If it is on the left of vertical, then we will show corresponding angle by negative sign, okay? And if considered ring is on the right side of the vertical, then corresponding angle we will show with plus sign. Got it? Fine. Now, tell me, when you just increase value of theta, right from minus alpha 1 to 0, and then after from 0 to plus alpha 2. Look here, minus alpha 1 to 0, correct? And then from 0 to plus alpha 2. Again, from minus alpha 1 to 0, you are increasing that angle, and from 0 to plus alpha 2, correct? So you can continuously increase value of theta right from minus alpha 1 to plus alpha 2. And if you do that, you are going to include all such rings continuously, which are arranged along the entire length of the solenoid, correct? And then after, if you are finding such integration, will definitely give you resultant magnetic field at considered point P. Got it? Fine. That's why the limits are from minus alpha 1 to plus alpha 2. Got it? Now, because this part is constant, I can take it out of the symbol of integration. Mu 0 ni upon 2 taken out. You know derivative of sin theta is cos theta. Derivative of sin theta is cos theta. Then integration of cos theta will be sin theta. Correct? But which are the limits? From minus alpha 1 to plus alpha 2. From minus alpha 1 to plus alpha 2. Correct? Now this part as it is. Come on. Instead of theta, you must place now upper limit, that is plus alpha 2. Put it here, sin alpha 2. After placing minus sign, instead of theta, you must write the lower limit, that is minus alpha 1. Minus alpha 1. Correct? And now don't you know, sine of minus alpha 1 is nothing but minus of sine alpha 1. That minus and this minus will become plus. So inside the bracket, it will appear sine alpha 1 plus sine alpha 2. And this part as it is. Correct? My dears, this final formula is not derived in the textbook. Just for your satisfaction and knowledge, I have given you complete derivation. Okay? Now for examination point of view, you may remember this formula directly. Okay? This is the formula to be used for finding magnetic field at some axial point inside the current carrying solenoid of finite length. Okay? Now in that solenoid, what is small n? Number of turns per unit length. Capital I is the current passing through that winding of the solenoid. And what are alpha 1 and alpha 2? Look, alpha 1 and alpha 2 are the magnitudes of angles made by vertical line passing through considered axial point. with the line segments joining point P and two upper ends of the solenoid. Okay? Those angles are alpha 1 and alpha 2. I repeat, alpha 1 and alpha 2 are the magnitudes of angles made by a vertical line passing through considered axial point with line segments joining point P with two upper ends of the current carrying solenoid. Got it? Fine. Now, same formula if you want to write vectorially, then instead of B you may write vector B. But don't you know, vector equals to magnitude multiplied by unit vector. Magnitude is this much. And what about unit vector? See, in this present solenoid, when you pass current this way, correct, through the entire winding, then you are going to have magnetic field toward the right hand side this way. That is in the direction of positive x-axis, and that's why I am putting unit vector I hat. Correct? Magnitude is same, but unit vector will be I hat. If at all you are passing the current through the winding this way, correct, then you will have magnetic field towards negative x-axis. At that time you may write here minus I hat. Got it? But how to find out direction of magnetic field produced on the axis of this current carrying solenoid of finite length? For that there is a rule, and that rule is known as right hand thumb rule. Right hand thumb rule. What is that right hand thumb rule? Very simple. Hold the axis of current carrying solenoid in the right hand palm such that fingers should take the turn in the direction of current. Correct? Then whatever is the direction shown by the thumb, which is parallel to axis, in the same direction we are going to have magnetic field. I repeat, hold the axis of current carrying solenoid in the right hand palm such that fingers should take the turn in the direction of current. In this condition, whatever is the direction shown by the thumb, which is parallel to the axis, in the same direction we are going to have magnetic field. Got it? When you pass current this way, come on, magnetic field will be towards positive x-axis. If at all you are passing current this way, suppose, then you must hold this axis in the right hand palm this way, then fingers are taking turn in the direction of current. At that time thumb is showing you this direction towards left hand side, that is towards negative x-axis. Got it? Fine. Now we consider a special case, and what is that? Considering infinitely long solenoid. If this current carrying solenoid is just imagined to have infinite length, theoretically, practically you can say length of the solenoid is very large as compared to the radius of the cross section of solenoid. If length of considered solenoid is very large as compared to the radius of cross section of the solenoid, then that solenoid is said to be very long. Okay? Theoretically having infinite length. Then what will happen? Look, if the same solenoid has greater and greater length gradually, then tell me this left end would approach this way, correct? And because of that, the magnitude of this angle will keep on increasing. Similarly, right end will move this way, and then magnitude of this angle will go on increasing. Finally, when both the upper ends reach towards infinity, by that time both the angles will tend to become 90 degree each, correct? So maximum values of these two angles will be 90 degree each. So for theoretically considered solenoid of infinite length, remember values of alpha 1 and alpha 2 are 90 degree each. Come on, alpha 1 and alpha 2, both of them are 90 degree for infinitely long solenoid. Just put those values here. This is 90 degree, this also is 90 degree. Sin 90 is 1, sin 90 is 1, 1 plus 1, 2, these two and these two will cancel, giving you mu 0 Ni. So at that time magnetic field will be mu 0 Ni. And because we are going to have same magnitude of magnetic field at each inside point in the infinitely long current carrying solenoid, we can say the inside magnetic field will be uniform. How would you represent uniform magnetic field? By magnetic field lines I am showing you. Consider this extremely long solenoid, okay? And for extremely long solenoid, this length will be very large as compared to this radius of this circular cross section, correct? Now in that case, when you pass current through the winding, at that time you will have magnetic field only inside, There is no magnetic field outside the extremely long solenoid. Whatever is the magnetic field, it is present only inside, and that inside magnetic field has such magnetic field lines in which you can say these lines are parallel to each other. Not only that, perpendicular separation between each two consecutive lines is same. So you can say it is nothing but uniform magnetic field, right? Having strength of magnetic field at each point same by this much magnitude, mu 0 and I, got it? If you have remembered, in chapter number 2, we had talked about uniform electric field, and how could you get it practically? With the help of very large parallel plate capacitor, in which the plates are very large, and compared to the dimensions of the plate, the perpendicular separation between parallel plates was taken very small. At that time, in the region between these two unlikely charged plates, we had electric field of this form, meaning thereby if electric field lines are parallel to each other and perpendicular separation between each two consecutive lines is same, this is nothing but uniform electric field. So remember, for having uniform electric field, you can think of such a large capacitor, and for having uniform magnetic field, you can think of such a long solenoid. Got it? Fine. Now my dears, we go for question number 7. It is about Ampere's circuital law. My dears, to understand about Ampere's circuital law, first of all, you just select some current carrying wires. You may show any number of current carrying wires. Here I have shown 7 current carrying wires. They are these wires 1, 2, 3, 4, 5, 6, 7. Correct? Now out of this 7 current carrying wires, I just select first 5 wires at present. Okay? Then after what I do consider, I just consider some planar closed loop which can enclose these 5 currents, and that planar closed loop is this. Why it is called planar loop? Because the entire loop is lying in the same horizontal plane, correct? Not necessary that you should consider only horizontal plane, not necessary, but you must consider that loop to be planar. Okay? That plane may be any plane, but it must be planar closed loop. Got it? Fine. This closed loop may have any sort of shape, no problem. Now such a closed loop which encloses given currents is given a specific name, and that specific name is Amperian loop. What do we call it? Amperian loop. Fine. Now, what is Ampere's circuital law? I am showing you now. First of all, you do one thing. You just consider the entire length of Amperian loop to be divided into extremely small length element vectors, which I have shown by arrows on this loop. Okay? Fine. Now the amounts of currents passing through these 7 wires I have shown by symbols respectively I1, I2, I3, I4, I5, I6 and I7. Correct? Now out of these 5 currents, suppose I1, I3, I4, they move towards upper part. Correct? I1, I3, I4. And I2 and I5, they move towards lower part. Okay, fine. I1, I3, I4 move upwards, and I2 and I5 move downwards. Okay. Now, here whatever is the resultant magnetic field produced by all these 7 currents is suppose vector capital B. Now, what you are supposed to take? You are supposed to take line integration of this magnetic field over this entire considered Amperian loop, and that line integration is shown mathematically by this symbol, closed line integration of magnetic field. that is closed integration of vector B dot vector dl. You know how to take it? First of all, each length element vector you should take that small, that small, that small, such that at least for that particular length element magnetic field can be taken as constant, correct? And then you should take the dot product between magnetic field existing in a given length element and corresponding length element vector, and then such dot products you must find out for each length element, and then after you should take their addition over entire Ampérian loop. Because that Ampérian loop is a closed loop, we just put here closed integration symbol, correct? But how much is that closed integration value? That was obtained by Mr. Ampère, and he got this result that this closed line integration of magnetic field comes out to be this much, that is product of this and this, that is product of permeability of vacuum and the algebraic summation of electric currents enclosed by considered Ampérian loop. When you say mathematically that this is equal to this, the same mathematical statement if you just utter in words, it will become statement for Ampère's circuital law. Ampère's circuital law. How would you give its statement? I am showing you. Closed line integration of magnetic field taken over considered planar closed loop in a magnetic field is equal to product of permeability of vacuum and the algebraic summation of electric currents enclosed by that considered loop, full stop. This very statement is called Ampère's circuital law. I repeat, closed line integration of magnetic field taken over considered planar closed loop in a magnetic field is always equal to product of permeability of vacuum and the algebraic summation of electric currents enclosed by that loop, full stop. This very statement is called Ampère's circuital law, correct? My dears, you must note now 2 points very carefully. First point, remember in producing resultant magnetic field in this region, all 7 currents have contributed, and because there is a contribution from each of these currents, we should consider all these 7 currents while finding out this closed line integration of magnetic field, okay? But then on right hand side, while finding sigma I, you should consider algebraic summation of only those currents which are enclosed by considered closed loop. If considered closed loop is this, then it encloses these 5 currents from I1 to I5, correct? Then you are likely to take the algebraic summation of only those 5 currents which are enclosed by this loop. At that time you must not consider this I6 and I7 because they are not enclosed by this loop. Got it? I repeat for the last time. On the left hand side of Ampère's circuital law, while finding resultant magnetic field, because there is a contribution from each of the given currents, we must consider all the currents, okay, whether they are inside the loop or outside the loop. Got it? But while finding algebraic summation of electric currents on the right hand side in the same law, we must consider only those currents which are enclosed by the considered loop. Got it? Fine. There is a limitation of this Ampère's circuital law. It is to be applied only for the steady currents. Only for steady currents. Steady current is that which continues to flow in the same direction with the same magnitude. It is called steady current. Okay? Fine. Now, question arises while taking this algebraic summation, which current should be taken positive, which current should be taken negative. I am showing you. First of all, you consider some right-handed screw whose axis is perpendicular to the considered planar loop. Consider one right-handed screw whose axis is perpendicular to the plane passing through considered Ampérian loop, correct? And then after, in the same manner in which you are taking the line integration, suppose this way, correct? Say clockwise. In the same manner, you must rotate this right-handed screw, right? And when you do that, naturally, When you rotate the screw this way, it will advance vertically upwards. If it advances vertically upwards, then out of these 5 currents which are enclosed by this loop, you should consider those currents which are flowing towards upper side positive, and those currents which are flowing towards lower side, you must consider them negative. Okay. So, if any current is flowing in the upper direction, then you must consider them positive, and in the same problem, these currents which are flowing towards lower direction, downward direction, you must consider them negative. Okay. So, remember, this is the sign convention for the selecting the signs of currents. Okay. Fine. My dears, it is not necessary that you should carry out line integration while traversing over this Ampérian loop in this manner only, not necessary. You may traverse in this fashion also, no problem, correct. At that time, if you rotate the screw in the same fashion, it will move vertically downwards. At that time, this downward current should be taken positive, correct, and at that time this upward current must be taken negative. Got it? Fine. Now we go for extra question regarding points of differences between Gauss law and Ampère circuital law. Very good question. This Gauss law you had studied in chapter number 1, and this Ampère circuital law we are studying right now in this chapter. Okay. Which are the points of differences between these two laws? I am showing you. First, mathematical form of Gauss law was this: closed surface integration of electric field taken over considered closed surface in an electric field is ratio of algebraic summation of electric charges enclosed by the closed surface to permittivity of vacuum. Correct? What is the mathematical form of Ampère circuital law? Just now we have seen, same format I have written here, no change. Closed line integration of magnetic field is equal to product of permeability of vacuum and the algebraic summation of electric currents enclosed by considered Ampérian loop. Correct? Here there is a surface integration of electric field, surface integration. Here there is a line integration of magnetic field. Correct? Third point of difference, here we can find out electric field produced due to uniform charge distribution. Using this law we can find out magnetic field due to uniform current distribution. Correct? Then here while applying this law, we just think of one closed surface which encloses some given amount of electric charge, and that closed surface is known as Gaussian surface. Correct? Here we think of that closed loop which can enclose given currents, and that closed loop is known as Ampérian loop. Okay? So here we think of closed surface which is called Gaussian surface. Here we think of closed loop which is called Ampérian loop. Here we are taking algebraic summation of charges enclosed by considered Gaussian surface, and here we consider algebraic summation of electric currents enclosed by considered Ampérian loop. Okay? So these are the important points of differences between Gauss law which were studied in chapter number 1 for static electricity and this Ampère circuital law for magnetism. Okay, in this chapter. Got it?